Hello everyone, welcome back to another discussion in dynamics. Plan for today is following. We're going to do example number 1, and then example number 2, and maybe 3. However, example number 3 is exactly the same as example number 2. So I have a trick for that, okay? We'll do example number 3 in 60 seconds, okay? And where are we in our timeline? Aha, we are here. Okay, we are continuing work energy methods. And I just want to let you know, guys, that you can let me know what you think about my work. Please go to this website, and there's like a short survey there. You can tell me what you like, what you dislike, and what do you think I should keep doing, and what I can change in here. Yeah. You have time till Sunday. Alrighty. Okay, so any questions? Thank you. If not, let's do example number 1. Yeah. And I would like to thank you guys for suggesting that I should send these drawings to you before the discussion. It will save a lot of time. So please familiarize yourself with the problem statement before we start our solution. Alrighty, since I sent them to you earlier, I'm gonna start talking right away. So what do we have in here? Aha, again, we have a system of particles, yes, because we clearly have two masses, yes, mass M and another body that weighs twice as much, yes. What else do we have? Oh, we have friction at this surface and this surface, yeah. At these two surfaces, we have friction. And little body is pulled by force F, and the bodies are connected to each other via a pulley structure presented in the picture. System starts from rest, and we have no values here. This will be a symbolic solution, yes? It will be a symbolic solution, and they ask us to express velocities as functions of position. And that position is absolute displacement, not relative. All right. So I prepared for you configuration A. So this is how our system starts. And after a certain time, yes, after a certain time, our system will be in this configuration, yes. Bodies, little body will move to the left, which will cause big body to move a little bit to the right, yeah. And that displacement is defined by this green vector, displacement S, and displacement 2S is exactly how much big body will move to the right. You can also see that red marker, yes, here. Yeah. Oh, shoot. Sorry. This red marker here, yeah. So this, I just marked the starting point, yeah, where bodies were at the beginning. Questions? Yeah. So without further ado, let's just start our solution. We will start, since we are in work energy method, yes, work energy method. We will start with this expression, T1 plus V1 plus U12 non-conservative is equal to T2 plus V2. And as usual in these problems, we will just start with finding these guys, one after another. Sorry, Sanam, I'm gonna write it here. Alrighty, I like easy questions because I know the answers for them. I'm gonna go for T1, okay? It's 0. Why? Because system starts from rest, yeah? Sys starts from rest. And you guys clearly see that subscript 1 corresponds to configuration A, subscript 2 corresponds to the other configuration, yes? Some arbitrary configuration B. Yeah, this is arbitrary configuration, yeah? You can write arbitrary, yeah? Arbitrary. Okay. How about these potential energies? Do we have springs in the system? No. Do our bodies change elevations? No. So I know the answer. It's 0 and 0. 0, 0. No springs in the system, bodies don't change elevation. 0. Alrighty. How about T2? Our bodies have a velocity at configuration B. So I can write in here that that will be 1/2 m v1 squared plus 1/2 2m v2 squared. Yeah, we introduced two unknowns in here. Yeah, but let's reduce it to one unknown. Yeah, because I believe that we can find exactly what we can find exactly the relationship between v1 and v2. Yeah. So I think that in here we have 2 ropes, and in here we have 1 rope. So I believe that this is correct expression. Yes. Yes, I think I didn't make a mistake this time. Yeah. So this is our relationship. Let's plug it here. And we will end up with this expression. That this is equal exactly to 9 divided by 2 mv1 squared. Great. 80% of the problem done. So now this thing. U12 non-conservative. So there is friction in the system, yeah? All right. And I actually and we can actually find this U12 and C for the entire system, okay? Exactly how we did on Wednesday, okay? We did it for the entire system. Why? Because for example, I see a rope in here, yes? So work of that rope will be 0, yeah? I mean, work of the rope. Work of the tension in the rope will be 0, okay? And today I just would like to show you why it will be 0, okay? So I just would like to calculate U12 non-conservative for 2 bodies separately, okay? I can do it. So I will just do U12 non-conservative for body 1 plus U12 non-conservative for body 2. Yeah, that property is called additiveness. So work is additive quantity. That means that we can the work of the done on the entire system can be actually expressed as work done on one body plus work done on the other body. Yeah, they add to each other, and we can do that. Okay. You can choose whichever style you want. Okay, so let's focus on body 1. Let's focus on body 1. Let's find this one. U12 non-conservative of body 1. So to do that, I think we should start with FBD. Yeah, FBD for 1. Yeah, for body 1. Okay, that little guy. Yeah, so I think I can draw that guy here. It has this guy attached to itself. Okay, so since I like easy questions, I'm gonna go for easy forces. So I think that there is mg acting on that thing, mg, and we have also some normal force. Let's call it n12, okay, because this is normal force between body 1 and body 2. I think that there is a tension, yeah, tension from that rope and tension from this rope, yeah. So it's exactly 2t. And our body goes this way. Yeah, this is our trajectory. This is our trajectory. And our body goes this way, ds. So there will be friction here, yes? There will be friction acting this way. And there is one more force acting on our system, which is, yes, okay, you didn't say it, but you show it, yes? It's applied force. Thank you. F. A lot of forces. And also let's put here TF12, okay? TF12, because this is friction force between body 1 and body 2. Okay, so that would be U12 of F plus U12 of N12 plus U12 of TF12 plus U12 of 2T. Yeah. This is so 4 non-conservative forces act on our structure. Yes. I skipped mg because mg is conservative. Guys, without even asking you, or I will ask you, what is this? 0. For the same reason as earlier. Yes. N12 is perpendicular to ds. Okay. So these values will be integral from beginning to end of f times ds plus integral from beginning to end of tf12 times ds plus integral from beginning till end of 2t times ds. Okay. Maybe let's replace that beginning and end with some numbers. What do you think, guys? What are the integration bounds in here? If I scroll up the board even, you can look at the picture here. So what should I put here? Great. And top limit will be what? S, perfect, everywhere, yeah? 0 to S, 0 to S, yeah. Thank you guys for helping, yeah. Okay, and F was constant, yeah? Let me scroll up. Yep, they told us that F is constant, a constant force F, Full's block, yeah? We like to integrate constant things, yes? So this will be just F times S. Yeah, the first integral will be F times S. Yeah, with a plus in here, yeah? With a positive sign, because F points in the same way as ds. TF1 is also constant, yeah? Because we have kinetic friction. And that means that TF12 is exactly mu k times N12. And you guys know that N12 is mg. So it would be mu k mg. Yeah, this is constant. Great, we like to integrate constant things. So the second integral will be again mu k mg s, yeah? And I made a mistake because it's not gonna be plus, it's gonna be minus, yeah? And how about 2t? T is also constant. That rope, that tension rope will also be constant. So we can write here 2ts, but also with a minus, yeah? Okay. That's it. Yeah. That's our work done on body 1. Okay, so not 80, not 100, but 90% of the problem done. Yeah, we must also find U12 done on body B. Yeah, body 2. Unless there are questions. Now, U12 non-conservative on body B. Body 2, sorry. Questions to what happened so far? Yeah, if you have questions, you can think of them. Even if you don't want to ask them right now, keep them in mind or think of some questions. I will open question slot for very soon. Okay, so again FBD, yes? We have to draw FBD again. So we will have that rectangle, and this is FBD for body number 2. So again, I'm lazy, so it will be 2 mg. Yep. I think that also this will be N2, okay, or N ground if you want to call it. Let's call it, I know, N2, okay? Because this is normal force between body 2 and ground. I think that there was one rope attached to our thing. There is friction. And this time, this is our ds, yeah? The ds. Let's call it ds2, okay? Because that ds is different than the previous ds, yeah? That ds is twice as large as the other one, yeah? So there is friction. TF, but not TF12, TF2. Yeah, this friction is different than the previous one. Okay, there are 2 more forces acting on our body, which are, question mark, 2 more forces act on our body. What are they? You must speak louder. The first blast forces on this one. Exactly. So there will be this force, N12. Yep. And there was also friction between our bodies, yes? And our friction, this black vector here, yes? It was pointing this way. So now it will pointing this way on that body. TF12. Okay. Yeah. Sorry, guys, for asking you such simple questions. Yes, I know that most of you know that, but I just must do it because I just must ask you those questions. Okay, sorry. Yeah, in case you think that what I'm doing right now, I know what I'm doing. Okay. Okay. Wow. So we have like a lot of forces acting here. Okay, we must write all of these integrals. Yes, U12 of TF12 plus U12 of TF2 plus U12 of T plus U12 of N12 plus U12 of N2. Okay, 2 last integrals, I mean 2 last things we know what they're equal to, yeah? 0, because of the perpendicularity, okay? Great, so not 5 integrals, but only 3. Let's do them anyway. I don't know, put it here maybe. And you are gonna go here. Okay, so we have integral from beginning till end, and later we will replace that a and b with numbers, okay? Of TF12 times ds2 plus integral from the same bounds of TF2 times ds2 plus this integral from a to b of t times ds2. Okay, guys, analogically to the previous step, what integration bounds I should put here instead of a and b? Anybody? Maybe somebody who was silent whole the semester. Yeah. How about you, sir, in the blue hoodie? Do you want to go for it? It's 0 to s, almost. Yeah, it's from 0 to s, but one number is missing. Yes, exactly. Yeah. And why? Because if you look at that drawing, you can clearly see this blue vector. Do you see this blue vector? So big guy, this guy, big guy, is moving by 2s. Yeah, that's why these are our integration bounds. Thank you. Yeah. From 0 to 2s everywhere. Yes, yes, yeah. I know that this guy moves s in the left, so that guy is going to move 2s. Yeah. And actually, this is important information for you, Anna. This is absolute displacement. This is not relative displacement. Okay, this is absolute displacement for a person that stays here. This person. Okay. Why I'm talking about it? Because on Wednesday we talk about relative displacement, the delta rel. Do you remember? Okay. So actually, at home, actually try to solve that problem for relative displacement. Okay. You should obtain the same answer, but it will just show you a different perspective on how bodies move. Okay. So in here I just solve it for absolute displacement, and that's why I separate these two energies. Okay. At home, try to do it for relative displacement and try to write it right away. Don't do that. Just calculate this right away. Okay, do not separate these two bodies. Is it clear? Okay. But it's like an extra homework if you want to do it. You don't have to. Okay, so what do we have in here? TF12 will be mu k and 12. Ah, exactly the same as last time, yeah? So that would be mu k mg, yeah? How about 2f2? That would be mu k times which normal force? The other one, yes? This one. And we should find that force. So I believe that if we sum forces along y, we will have n2 minus n12 minus 2 mg. And this guy from part A was mg, yeah? And this must be equal to may, but ay is 0. So this is 0, yeah? So you guys can clearly see that our n2 is equal to 3 mg. Yep, that normal force would be equal to 3 mg. So that would be equal to 3 mu k mg. Awesome. And it's constant, by the way. So the first integral will be equal to mu k mg times 2s. Second integral will be equal to, okay, I made a mistake, but I will correct myself in a second, will be equal to mu k 3 mg times 2s, yeah? And what I forgot about, minuses, yeah, as always. Minus and minus. And the third integral will be with plus, yeah, because t points in the same way as ds2. So that would be plus t times 2s. All right, 100% of the problem done. Because we found these 5 guys, yeah? So this is our work done on body 2. Questions? we are just repeating steps, yeah, from Wednesday and Friday, yeah. Think about questions, and in the meantime, I will just plug everything back to our original equation, okay? So let's do it. Plug everything back to this equation. This equation. So I bet that we started with 0 plus 0 plus, these two guys right now. So we had there Fs minus mu s, mu k mg times s minus 2ts minus this thing. Yeah, I'm just gonna copy it. This thing, which is very big. And I did all of that just to also write right-hand side. So at the end, we will have 9 divided by 2, m v1 squared plus 0, yeah? So this is one long equation, yes? And we did all of that, I did all of that, and you helped me, just to show you that indeed, this thing cancels with this one, okay? The internal forces really canceled out. They don't do any job. That's why we don't have to include them. Yeah, we could actually skip them in this solution, but I just wanted to show you that this is why we skip them. Okay. So I think that they ask us to express V1 as a function of position. Yes. If I scroll up the board, this is exactly what they ask us to do. Yeah. And I think that this equation will help us to do that, okay? So just express this guy. Oops. My computer doesn't listen to me, but now it listens. In terms of this guy, okay? Let's do it. If you do some algebraic transformations, you will end up with following expression. V1 is equal to square root of 2 divided by 9m times f minus 9 mu k mg times square root of s. It is clearly some function 1, yeah, of s. By the way, they also ask us to express v2 as a function of position, yes? But v2, sorry, but v2 is 2v1, yeah? So I can just write 2 in here and copy this. And I can claim a victory, yes, over that problem. Because this is clearly some function of position. This is just f2s, yeah, okay, and this is the answer. I see your hand, just okay. That's it when it comes to this problem, and now time for questions. And I saw one hand. That's a great question. So I solve problems in magnitudes. So usually I give answer in magnitudes, and then I write find the directions in the picture. So I solve for magnitudes, and the directions are showed here. This die goes left, this die goes right. Okay. But if you want, this is just my style. Yeah. If you prefer developing better style than mine, which is probably easier, go for it. Yeah. It is possible to end up. It is possible to end up with this value negative. However, I don't like it. Yeah. I hope I answered your question, Isabella. Yeah. Thank you for being nice. Yeah. Okay. Any other question? How do you like it? How does it look like from your perspective, guys? It's digestible? Yeah. Yeah. Maybe try at home the other way. Yeah. Just try to solve it for the entire system. Yeah. That thing for try to write U12 non-conservative for the entire system. Yeah. Maybe this will like help you. Okay, I like that problem for some quirky reason. I don't know. It's a good problem. Yeah. Okay. Example number 2. Let's do it. As usually, please familiarize yourself with the problem statement before we start our solution. Alrighty. So this example just introduces this expression. Yeah. Efficiency is power out divided by power in. That's the only new thing you're gonna see right now. Okay. Efficiency is P out divided by P in. And maybe this one, yeah. Power is force dot velocity. Okay. And what do we have in here? First of all, they ask us to find maximum velocity that this body can have. And by the way, that velocity is constant. And what do we know? Aha, we know mass of the body, which is usually known. We know geometry, so we know the angle of the incline. We know G, and we know that there is a friction between body and the ground. Also, we know power of our motor, yes, which is usually good to know. And we also know its efficiency. Okay, so we know everything about the system, and we are just wondering how fast we can pull the stuff up the incline, yes? That's a question. All right. So what would be P out? What would be P out, guys? First of all, this is our P. P out is equal to efficiency times P in, yeah? But it also can be expressed times as some force. You're gonna tell me in a second what force times velocity of our body. Okay, and I just would like you to tell me what I should put in here. And I will give you a hint because I will just draw free body diagram here. Okay, FBD. Okay, so we have mg acting on our system. We have normal force. I think that we have some friction here. And I also think that we have tension in the cable, yeah? That's it. That's it, yeah. So which of these 4 forces should go here? What do you think? And why? I don't know, is it appropriate if I tell you that I love you? Maybe yes. Okay. Yes, that's correct. That's correct. Thank you for your help. Yes, exactly. I'm going to put T in here. Yeah. T in here. Because this is exactly what our motor generates. Perfect. This is P out exactly. Yeah. Okay. So let's find that T. Let's find T. So I think that this is our trajectory. Yes. This is our trajectory. I should come up with like abbreviation for trajectory, maybe traj from now on. Okay. This will be trajectory. No, I like trajectory. It's a good word. Trajectory. So let's just project mg very quickly. So this guy will be mg sine theta. This guy will be mg cosine theta. Okay, sum of forces along this direction. Let's say whatever letter you like. I don't know. Let's say p direction. No, p is taken. So let's say xi. No, let's say xi. Okay, let's do Greek letters. Or choose whatever letter you like. Along this direction, that would be t minus tf minus mg sine theta. And this is equal to ma xi. And what is ma xi? Sorry, what is a xi? It's 0, because our velocity is constant. Yep. So we just found expression for t. T is equal to tf plus mg sine theta. Okay. Questions to what happened so far? I'm speaking a little bit too fast maybe today. Is it okay? The pace is good with you guys? Yeah, thank you, thank you. Yeah. I see that many of you are confused with that letter. Let's use alpha, okay? So, okay, this is direction is alpha. Next week we'll use Egyptian letters, like those birds or something. I don't know. Do you know the hieroglyphs? Maybe some of that we should use. Yeah. All right. So what's the next step? Let's put everything in the boxes into this equation. So this thing should go here, will go here, and this thing will go here. Okay? So we will end up with, and by the way, also before doing that, you can clearly see, guys, that this will be t times v. Yes, because our t is aligned with velocity. I hope you can see that, yeah? Our t is aligned with velocity. Yep. So now we will end up with epsilon p in is equal to tf plus mg sine theta times velocity. Oh, and also tf. You see, guys, I forgot about that. Of course, it's a kinetic friction, yes. So tf will be equal to mu k times n. So that means that that would be equal to mu k mg cosine theta. Yes. So let's plug this one as well. Epsilon is P in equal to mg cosine theta with mu k here, plus mg sine theta velocity. Okay, and they ask us to find expression for velocity, yeah, max velocity. So I mean, you already see it, yeah. So velocity will be equal to mu k mg cosine theta plus mg sine theta, and in here we have epsilon per in, and these are all known values. Okay, this is the solution. Yeah, so when it comes to efficiency problems, I don't have a recipe. I just look at this equation, I look at that equation, I look at this equation, and then I find everything. Okay. I still have you for 1 minute, so if you please don't make sound right now with your backpacks. Yes. Exactly 40 seconds. Yeah. Okay. Any questions to that? Yes, Bryce. You mean here? No, because it's negative here. Yeah. No worries. Yeah. So I'm just gonna copy that equation very quickly, and we will solve the other problem in exactly 10 seconds. Please familiarize yourself with the problems. I'm kidding. This is exactly the same problem. Okay. You can familiarize yourself with this problem at home, and you will see that this is exactly the same problem. The only difference is that they ask us to find mu k instead of v. Okay, so what I wanted to do, I just want to copy paste here what we found on the other board. Okay, with one caveat. Yeah, instead of epsilon p in, we are just going to use p out. Yeah, instead of that, we're just going to do that. Okay. Then a little bit of algebraic transformations, and you will end up that mu k is equal to some expression 1 over cosine theta p out mg v minus sine theta. Plug in values, grab calculators, and find mu k. Okay. Okay. So we did 3 problems actually. Thank you for your time. Sorry for stealing 1 minute from your time. And one more thing, make sure you enjoy your weekend. Okay. Bye.